Hi everybody, I'm Scott Hawley. I'm at Belmont University where I teach mostly audio engineering students. And actually it was my first AES in 2013 where I first heard about machine learning when Elias Kokinis of Acusonis spoke right after me and blew my mind. Our topic for today is learning to model audio effects. A couple products out there that you may be familiar with, the Kemper Profiling Amplifier and Fractal Audio has their AXFX. And both of these systems can learn to replicate certain sounds. Fractal has a whole bunch of what we might call basis functions that it can adjust parameters for. And both of these systems are in heavy use. Recent webcast from Doug Doppler had top guitar techs from around the world, and you saw a lot of Fractals and Kempers. But what if we want an effect that's not on the list? If we want to try to learn effects, how general can those be? Could this be a way of modeling effects and allow users to model their own effects or even invent new effects? Some work that we've been doing on this in the area of black box modeling, we call the model signal train for trainable signal chain. And this was last year at AES. Myself, Ben Colbert, and Stylianos Mimilakis had a paper. And then coming up next month, you'll get to hear from Billy Mitchell on some more work we've done. And I'll share my slides so you can follow those links to listen to audio samples. Basic idea is you have some audio effects unit or physical process, and it has some maybe adjustable parameters on it. And you want to be able to put input audio into it and look at the output audio and then try to mimic that by minimizing the difference between the output of some neural network with that. And so we want to try to go for general audio effects, nonlinear, time-dependent effects. We want to be able to learn what these knobs are and what they do. And in this case, we're not so interested in making a generative model, even though those are very interesting. We're more interested in capturing what this effect or process can do. And just for the interest of time, there are other groups working on this, Marco Martinez and people at Queen Mary in particular, lots of other people. Just in the interest of time, I'm going to stick to what we've been doing. Basic model architecture is we have input in the waveform domain and output in the waveform domain. And in between, we convert to spectrograms in terms of magnitude and phase. It starts off as a spectrogram, but actually we let that evolve as the neural network learns. And then the controls or the knob values, we stick those into the middle. These are autoencoders that are actually done as fully connected layers. And then the original input and the output from these layers are merged. In the case of phase, it's a skip residual connection, what we might call a wet-dry mix in audio. And for the magnitude, it's a skip filter, which is kind of like a gain. So this has similarities with UNet and WaveNet, if you're familiar with those. One other thing I should mention is that we have a look-back buffer where we don't try to output the very beginning of the input audio. Some effects are harder than others, and if something's happening in the moment, like distortion, that's usually pretty easy. 4 years ago, I got really excited about this work just from the different kinds of distortion that it could learn. But compressors were hard. And so we ended up spending a lot of time working on just compressors. More recently, we started branching out into some other effects. There are lots of interesting effects to model. One of the issues we've been having is just trying to get the noise down. So Billy's paper this year is all about noise. And then also for practical audio production, we really do want to have CD quality or better sample rate, which is going to mean long sequences, which can be a challenge. Now, if you want to look at modeling of other effects, Marco et al. Have already done a lot of interesting effects without knobs on them. Again, I'm going to stick to our work. A couple other effects I haven't published about, but I've showed at talks, are these sort of inverse effects, like denoising, lots of things. So you could send some good input and add noise to it and then reverse the order of them and get a tunable denoiser. Or in particular, this thing can learn time alignment. So you can start with audio that's on the grid, mess it up, make it go off the grid, then reverse the input and output, and the model will learn to put things back on the grid. So it can do drum editing. So if you're late, if this line is on the grid, it'll bring it on. Now, if it's early, if you've ever done editing on your own, you know you have to put in a cut and then move it back and then fill in the silence with, say, time stretching or something. In this case, the model actually learns to synthesize more of what went before. So we're really excited about that. So I promised I would try and help people in audio get up to speed with attention, which showed up in natural language processing for language translation, image captioning, and speech to text. But a lot of people in the audio world still find it confusing. Previous methods before attention would use a sort of encoder and decoder architecture where you'd say you're translating English into French and all your words would go into this context vector and then they would get decoded. And the problem was if you had really long sequences, maybe this context vector wasn't big enough to hang on to all the information. So the idea was, let's connect up the inputs or the input states with these decoder states. And so you end up having a weighted mask that goes into the context vector, and you can hook this up to later decoder states as well. A lot of times you'll see these graphs showing, say, input and output and the attention weights, or showing the alignment between, say, words in French and words in English. They pretty much line up, except for, say, adjectives get reversed. Or in speech to text, there's a lot of good alignment. And this is relevant because attention is essentially a soft, differentiable version of alignment. That's a statement by Lucas Kaiser, who's a co-author on this other very important paper, Attention is All You Need. And their model is called Transformer. So earlier models had added attention to some recurrent or convolutional architecture. With attention is all you need, just use this fully connected or feed-forward attention and then add some other things. And when you do that, in particular taking out the recurrent neural networks, you can operate on whole chunks at a time in parallel, which makes it a lot faster. So a few features of this: positional encoding, we'll talk about that next. We've got feed-forward layers, skip connections. Not shown in this are query, key, and value matrices, which we'll talk about a little bit later. So the positional encoding, once you have the fully connected layer, in order to give it a sense of positional structure, they added some extra, what we might call channels, to sort of encode where along the sequence things are. And the particular way they chose to do it was using a set of sine and cosine functions, which later, when they end up showing up in dot products, ends up being akin to a Fourier transform. One of the problems with these attention weights is, let's say your sequence is n samples long, so you're going n to n, you end up with n squared weights, which can get expensive. So this year we've seen some models that attempt to mitigate that by either kind of breaking it down into windows, or windows that kind of have some gaps in between, or some combination thereof. They can do long sequences, which for text, the largest I saw was 64,000 tokens. In terms of CD quality audio, that ends up being about 1.5 seconds, which is good, but for example, in LA2A, release time is about 5 seconds. Some similarities between the transformers and signal train. I mentioned this positional encoding is kind of like a Fourier transform. We've got these fully connected layers operating globally or within windows, entire chunks at once, long sequences, different ways of doing that, and time alignment. Now, one thing that these transformers will do, they'll have these QKV vectors, which again, I think people in audio find confusing. But essentially, we're trying to answer the question, if attention is a weighted sum, how are we going to do the weighting? And so if the query is like our possible output, and the key and the value are related to our inputs or the hidden states on the encoder, then what we do to get our attention scores is we take a dot product between the query and the key and use the transpose just to make the dimensions come out right. What you end up with is a square matrix with values between 0 to 1 that sum to 1 along rows. In other words, these are weights. So essentially you do summing on the values, which are like the inputs, using those weights, and that'll get you your context vector, and you can move on from there. So if we want to add that to signal train, I found that a little confusing, but in May, Francois Fleuret posted this great attention toy 1D model where he's doing something kind of like audio sequences and showing different ways to manipulate that. And so I took what he did and converted it from convolutional layers that he was using to fully connected layers. And when we do that, so red is the new line, black is the old signal train, and with attention, the loss ends up being quite a bit lower as a function of how many iterations you do. Now, it still ends up at about the same noise value that Billy and I have been butting our heads up against, but it gets there faster. In fact, it gets there about 3 times faster overall. Now, as far as that error or noise, you'll have to stick around for Billy's talk next month at AES 149, or ask me some questions during the Q&A. Also, for people who are interested in learning how to do machine learning in audio, Ryan Miller and I maintain a page on GitHub called ML Audio Start that has links to tutorials and online courses from lots of different people. And we've got contributions from people all over the industry. So I invite you to check that out. And with that, thank you for your time. Enjoy the rest of the symposium.